These data represent 6 measurements from 6 different samples using survey type data. So we don't have good energy resolution, but we do have signal that comes from a range of different elements. So we've got sodium, oxygen, this is a sodium Auger, these are sodium 2s, 2p, bit of oxygen there, that's the carbon, and given this pattern of peaks, we would like to identify, using these survey data, what the chemical composition might be. And the analysis that is performed using these survey data is to construct 5 component spectra. These columns here are component spectra that have been calculated from the data set as a whole. So these other 6 survey spectra have been used to construct these spectral forms, and these spectral forms are hopefully, and you always have to be hopeful of this, hopefully showing us some chemistry. At the end of the day, these are vectors that have been calculated from the original survey data, so you always have to bear that in mind when you do an analysis of the peak structure within these. And it could be that we've chosen badly the spectral forms, the shapes that are calculated. This is not a unique solution. There are other possible solutions. This is just one of them. So to try and evaluate at least one of these, we will put some quantification regions on, at least in the first instance. And we have an element library that has Schofield cross-sections that have been corrected for escape depth, and we will use peaks that are at high kinetic energy, relatively high kinetic energy. Although the sodium 1s is more intense, what we're going to use is a sodium 2s, which is this one here, to do a quantification along with the carbon and the oxygen. This is a better cluster in terms of kinetic energy, so any corrections will have a smaller effect on the quantification results. So having clicked, we're going to create here a region, and similarly we will create a region on the carbon 1s, and also on, this is the oxygen 1s. I won't zoom this time because I've zoomed in, and what I'm going to do is create a region that, unfortunately for the oxygen, includes structures here and here which are related to this sodium Auger. So although I've now got 3 regions, and if I put up a quantification report, the quantification property page on the annotation dialog window, I'm going to select a new option here that says both from the active tile. And what this will do is it'll gather quantification information only from the spectrum in the active tile. These other options on the quantification will use a selection that you make in the right hand side. So depending on what you select here, that will determine the type of table that is generated if I use any of these other table types. But when I say from the active tile, it's only going to take it from the spectrum that you're looking at. And I'll press apply. So right now I've used both because I already know that the oxygen contains peak structure. I also know that the carbon contains peak structure, so it's my intention to develop not just a quantification based on regions. I want to use components as well, hence I've gone for both. And I've used the active tile only because I want to be able to keep this table constant regardless of what's selected in the right hand side. So given all of that, let's zoom in and create now not regions, we're going to add some components. So once again, I've got the component property page topmost, I've got the element library, and I've got create when line selected. So what I'll do is I'll click where I see the oxygen, and when I click here it's going to create a component. Let me use the region to zoom in. Then I hold the shift key down so I can adjust the width of this component. And having created one of these, I need to now create two more. At least two more. Let's move that one over here. And we'll say fit. So while these have all come up as oxygen, these are not oxygen. This is sodium KLL, and that should not be part of my quantification. And the same will be true of this one. And similarly for this one. So I've got, these are all Auger peaks. They should not be part of the oxygen signal. So I've now got a quantification where, and let me just illustrate this, that I'm going to call that now O1S region, and I'm going to call this O1S component. So you can now see that we've got a component here that is delivering the amount of oxygen as opposed to the region, and that was the function of selecting the quantification option where it said both from active tile, both meaning both components and regions. So I need to do a similar creation for this carbon 1s. That is to say, I need to create using the components property page topmost and create when line selected. Clicking on the carbon 1s will create two peaks in this carbon 1s in this carbon 1s spectrum, and these will have the appropriate RSFs, and this is, I believe, to be a CH type peak, and this one is a CO. And once again, instead of using the region that was previously used, it is now, because there are components defined on this region, it's using the component intensities rather than the region itself. So now we can see we've got, let's see, we've got the CH peak is about 19%, the CO is about 15%, and the oxygen is somewhere around about 40%. So we seem to have something based on these that is looking more like we've got, well, this is a very rough estimate. We'll say this looks more like CO3 Na2. Now that's just a rough guesstimate based on this component. So having observed that I've got something along these lines, I might go back to my original calculation and look more closely at the component that I chose for this, where I saw a pair of peaks like this, and I would like to see whether I can get some spectral form that would look more like what I'm anticipating based on this rough quantification here, and then calculate, if I assume that, the other spectral forms and see if I can get a self-consistent answer. We have a set of measurements that were taken from several different samples, and these have all been saved as separate VAMAS files, but we can load and merge these so we can then do some comparisons between the different data that have been collected. If we look at the carbon 1s that is, you can see that we have a range of different carbon chemistries within these data, these different samples, but we have survey spectra that give us not just the carbon 1s, it gives us more information about a sodium peak, and we've also got oxygen, and there's the carbon, and these are essentially sodium, carbon and a few little other minor traces, these aluminium and various other elements. But what we're really interested in is trying to understand this carbon chemistry here, and you can even see within the survey spectra that you've got a range of different carbon chemistries. So the normal thing would be to start to do peak fitting on the carbon 1s spectra. What we'll try and do is a decomposition based on the survey spectra, so we can give some insight into what might be here in this carbon 1s. So bringing up the spectrum processing dialog window, I've overlaid in the active tile two of these survey spectra, and I've selected these because I've looked at these data normalized, and I've decided that this is the sodium Auger peak and it's reasonably well aligned. And similarly, when I look at the sodium 1s, again we have a fairly good alignment here. And then the final test will be to have a look at the sodium 2s, and if we just expand this, you can see this is the sodium 2p. This is an oxygen 2s over here that's interfering with the sodium 2p, but you can see that the alignment is reasonably good throughout the entire kinetic energy range, and this is what makes this a good pair of spectra to look at. We've also got some variation, and you can see that the background is different here, the relative amount of carbon is different, and the sodium, well, let's have a look more closely at this. Yes, there's a difference in the sodium peaks as well. So, having decided we've selected these two spectra, what I'm going to do is perform a difference spectra calculation, and this gives me a range of different survey spectra that are a blend between the first and the last in this list, and the first and the last in the list are the two that were overlaid in the active tile when I pressed the difference spectra button. And what I'm doing is I'm scanning through these data, these difference data, and I can now see that something is happening here in the carbon. So it would appear there are a pair of carbon peaks forming in at least one of these different spectra, and I can see that we've still got sodium, and that looks like a reasonably well formed sodium 1s, and that's the Auger for sodium, oxygen 1s, and this shoulder here is related to this Auger sequence here for the sodium. And again we've got sodium peaks, some oxygen, so everything is being determined from this different spectrum to have spectral features that look reasonably consistent with what you might expect from a material. But the thing that is really interesting is this structure here. So what I'm going to do is take a copy of that. And then I'm going to carry on and look to see what kind of spectral shape can be determined from the same difference sequence that will be the complement of the spectrum with the two carbon peaks. So let me have a look more closely at these. So we've got this, it looks like a very small sodium Auger, that's the oxygen 1s, that's a carbon 1s. And the carbon 1s, well, that has a completely different shape from the other spectrum that we identified. And to go along with that sodium Auger, there's a little bit of sodium here, that's the oxygen Auger. And then we have, again, a set of peaks that are related to aluminium and the sodium with a bit of the oxygen 2s here as well. So that looks like a plausible spectrum. And I will take a copy of that. So now I have, from my difference list, I've identified two spectral forms which are potential candidates for understanding the original data set. And And so you can see that there are two different shapes for this carbon 1s. So we will take this through, and I will also copy these survey spectra and we'll put them in a new file. So I've got the two different spectra here, and these are the ones that I want to find out how well these two different spectra, when I use them in a least squares approximation to these survey spectra, how well that these two can represent all of these 6 survey spectra. So I've overlaid in the active tile the two basis functions. I've selected the target spectra and I do generate spectra. And what this will do, I'll just turn off the normalization so that we can do a comparison. I used these two spectra were used in the calculation. So this is a breakdown and it's reproduced the original data exactly. That's what you'd expect. And that's the other spectrum that I used in the calculation, and that's reproduced the red spectrum exactly. And when I look at these others that weren't used in the calculation, I find that there is a difference occurring, and the difference is here. So that green spectrum is the least squares solution that's based on these two basis vectors, and the red one is the original data, so you can see there is a deviation here. So let's have a look at these deviations. That's what we saw. So let's go up, exact, a deviation, and then a deviation. So let's first of all eliminate a minor deviation. That these here seem to be very close, so let's calculate now a difference sequence based on the raw and the least squares solution. And the idea is that I need at least one more basis function in order to remove that difference that I observed in the least squares solution, where I used two basis functions. So what I need to do is identify another spectrum that looks like it could well be a spectrum measured from this type of sample. So there's one. So let's now go back. That's my original data set. Okay, so now if I copy this, I now have 3 basis functions, not 2. And I'm going to apply the same calculation. So 3 basis functions, select the target spectra, these are the original survey spectra, and then we will generate another set. And that's the first one, which had a variation before. So I used 2, 3, I used 4, and I've got a small difference here in 5, but that's a fairly good approximation now to using 3 basis functions. I've now got a reasonable approximation for, in fact, 4 of them. So I've got 3 basis functions, 4 that are well approximated, and then I've got another difference here. So let's try again. Let's overlay these, and again we'll go through and calculate the different spectra. So I'm working down the list and I'm looking for a spectral form that looks plausible in terms of spectroscopy. So the peaks shouldn't have distorted shapes. And what I would like to do is again use this within the calculation of a least squares from the original data set. So that's a sodium 1s. see what these look like. I just put up a grid so I can see where 0 is, and that helps me to make sure that these low intensity signal are not going negative, because that would not be a suitable solution. I want to have all positive peaks and background. So this looks like another possible candidate, so let's again take that through to the file and save. So now I've got 4 basis functions. I'm going to repeat the calculation once again, and so that's the first one. Now I get a good result, good result. So I've now got 4 basis functions and 5 spectra, all of which are being reproduced very nicely in terms of these least squares solutions. So let's now go to the final one, the first one, that is, where there's a discrepancy. The green one is the least squares solution, the red one is the original data, and because there is the least squares solution cannot properly represent the original data, they don't overlay perfectly, and so this is the thing that allows a calculation of another different spectrum, which will hopefully work out the difference between these 2 spectra, and once we've done this we should get a good representation based on 5 basis functions for all 6. Now ideally you would like to have 26 spectra against which you would measure, you would reproduce using these different shapes, and that would give you confidence that you had chosen wisely and that these were in some way component spectra that represented the entire set of measurements that you performed. So let us again go through here and try and choose So what I'm doing is I'm just trying to see what kind of influence the sodium is having. So that's the sodium 1s. And you can see there's an Auger peak here. So the fact there's a sodium Auger peak, when I've managed to remove the sodium 1s, well, this is characteristic of that first spectrum, and the quantification of the first spectrum did show that there was an anomaly between the sodium 1s and the sodium 2s. So it's not surprising that I can get rid of this sodium 1s while still maintaining a sodium peak up here. This is now becoming less chemically meaningful and more of an abstract type vector, but nevertheless it's the kind of information that's required to reproduce that first spectrum. So what I'll do now is go back, and again I'm going to copy that into the data file containing the original data and my basis vectors. So I have basis vectors here, and these are my target vectors. So let's do the PCA and generate spectra again, and this time we should come up with a solution that satisfies all of these. So we've got 5 basis vectors that are reproducing 6 different spectral measurements. The original data were measured from 6 different samples, but we only need 5. So if we can find one of these that contains all of the basis functions, and that makes sense, it's the first one. If I overlay these and I perform a little calculation based on these 5, well, that's the first abstract factor, second, third, fourth, fifth. So what we have are a set of abstract factors that look like we've got a significant shape, and then a difference to that significant shape, again a third difference, so we'd expect to find 3 significant differences between these spectra, and then that one looks like we may have a little bit of a shift. These look like derivatives to peaks, so that may just be there's some sort of, that's a clear difference type shift, so that suggests maybe we're accommodating some charge shifting between these different spectra. And the last one, well, there's clearly some kind of shape structure here that indicates there's a little bit more going on than mathematically than chemically. So let's just put these back, and we now have a solution which we can now see that there are 2 significant shapes here that we ought to understand the chemistry of these and maybe a bit more.